I promised that we would look very quickly at Fourier analysis. And as I said earlier, conceptually this isn't actually terribly difficult. Mathematically, getting this right in terms of maths is considerably more complicated, surprisingly more complicated. What we're looking at is the frequency domain. What does that mean? Let's just move on, shall we? Let's go in the opposite direction. We can create a signal. This black line here is our signal. And as you can see, we've got a peak here, and then it goes down, and it drops down, and then suddenly drops to a minimum, and then sharply up again, and drops down. And that looks like a pretty complicated signal. But it's a construction. It's made up of all of these colored lines in the background. So I've just simply done this in Excel, where we have the X value along the bottom here, and then I take the sine of that. Obviously, this is there's a little more to it in Excel, where you have to go to switch to radians and so on. But this is the basics of this. So sine X here, and then we have another curve, which is sine 2x. So first we take whatever x is, multiply it by 2, and then calculate the sine of that. And then similarly 3x, take x, multiply it by 3, and then calculate the sine of that, and so on and forth. And then the black line is simply the sum of all of those. And we can plot each of those lines individually and plot the sum there. So you can see here that we can create this complicated signal from these very simple basic sine waves in the background. Each of them is a simple signal, a simple sine wave, varying smoothly and continuously, as the sun does as well, but in a simple manner. So we have this signal. We've created this signal from a collection of sine waves. That's kind of the frequency domain. We can say that the signal contains all of these different frequencies. It contains this first frequency, and that second, and that third, and that fourth. They're in there. They're part of the sum. When we add them together, we're adding all of those frequencies together to create this more complicated signal. So what Fourier analysis will do is it will take a signal and it will break it down into those simple sine waves. You take a more complicated signal, something that looks very difficult to understand, like in this case, this black line here, which is even more complicated. You can see the functions I've used there to create it. We add them together. We then break that signal down. We look for the components of these in the original data. So we take our original signal and transform it into a set of different frequencies. Now that's great in many respects. You might be wondering, what am I going to do with that? Well, if you then can recognize what these signals are, these components of the signal as a whole are, then you've gained some information. Why do I have a peak there? Well, that's this particular signal reoccurring. Now, this might be something in a spectral signal. It might also be in your topography. Maybe you're looking for something that's occurring at different frequencies across a landscape. A collection of different processes occurring at different frequencies, whether it's tectonic and then slope processes, something like that. So you get a different landscape. You get variations in your landscape due to the summation of these different frequencies. So that's how Fourier analysis works. It's not magic. It's actually really quite smart, smarter than I am. But that's the basics of what it looks like.